When standing at the intersection of machinery and mathematics, where every vibration tells a story. Complex time waveforms are the language of these intricate tales, the traces generated by moving parts, revealing hidden signs of performance, wear and fault. To explore this, let's begin with the fundamentals. A time waveform is a graphical representation of vibration amplitude versus time, capturing the real-world movements of a machine as measured by sensors. Simple waveforms depict steady-state motions, a smooth sinusoid representing a balanced shaft, or a repeating pulse for periodic impacts. However, machinery rarely stays simple. As systems interact, loads vary, and defects develop, the time waveform transforms, becoming complex. What makes a waveform complex? Multiple frequencies, modulations, impacts, and irregularities blend together, forming patterns that are difficult to interpret by eye alone. Imagine the superposition of sine waves, random noise, bursts of energy, and amplitude variations. Each element precisely encodes operational characteristics and potential problems: unbalance, misalignment, looseness, resonance, or bearing issues. Through these signals, we gain access not just to visible symptoms, but to the invisible roots of emerging faults. To decode a complex waveform, interpretative tools are required. Begin by examining the shape. Sharp spikes indicate impacts, repeating rhythms suggest periodic events, modulated amplitudes may highlight resonance or variable load. Expert analysts often use zoom, scaling, and statistical review to unpack these patterns, identifying subtle changes that herald evolving machinery health. But complexity isn't only a challenge, it's an opportunity. Rich data, once unraveled, delivers insights unattainable by simple spectra alone. Metrics such as crest factor, kurtosis, and RMS aid in quantifying these signals. Crest factor, the ratio of peak amplitude to RMS, distinguishes impulsive events amid background noise. Kurtosis measures the sharpness of peaks, often enhanced by faults like bearing defects. RMS provides overall energy, reflecting the strength of vibration. When combined, these metrics transform the waveform from a chaotic pattern to a source of actionable intelligence. The relationship between time and frequency reveals even deeper truths. Complex time waveforms often correspond to intricate spectra, multiple harmonics, sidebands, and modulation products. Using tools like fast Fourier transform, we convert time domain data to frequency domain information, yet the complexity in the time signal sometimes exposes faults missed in spectral analysis alone, especially those caused by transient or non-repetitive events. Complex time waveforms are essential in diagnosing difficult cases: gear defects, electrical problems, or machinery with variable speed and load. By learning to read these signals, you gain precision in fault detection and predictive maintenance, safeguarding reliability and efficiency. Consider a practical example. Visualize a waveform from a rolling element bearing. The time trace shows occasional sharp spikes, rising above a background hum. These spikes, further analyzed, may indicate impacts from a spalled bearing race or debris. Meanwhile, sidebands, or amplitude modulations, imply passing frequencies from related components. Layering these clues, you construct a narrative of machinery health, leveraging your mastery of waveform interpretation. As you progress, combine waveforms with supporting diagnostic tools. Use phased time samples to synchronize events. Overlay signals from multiple sensors to compare axial, radial, and tangential motion. Employ advanced filtering to isolate specific frequency ranges, extracting the most relevant features for analysis. For professionals and trainees, this skill is invaluable. Navigating complex time waveforms equips you to detect early faults, assess severity, and prioritize corrective action. It encourages a proactive rather than reactive approach, reducing downtime and extending equipment life. To summarize, complex time waveforms are more than tangled traces. They are gateways to advanced machinery diagnostics. By understanding their features, metrics, and interpretive techniques, you transform ambiguity into clarity, making confident, data-driven decisions. Approach each waveform as a puzzle, and over time, you will develop not only greater technical skill, but also professional confidence. Continue to explore, practice, and refine your interpretations. As you master the art of reading complex time waveforms, you become an essential guardian of machine health, capable of translating vibrations into impactful solutions. Embrace the challenge and step forward confidently. Your expertise begins here.